to the second episode of our online seminar on Monte Carlo. It is my great pleasure to introduce our speaker today, Professor Mike Giles. Mike is a professor of numerical analysis at the Mathematical Institute, University of Oxford. He has made significant contributions to scientific computing and Monte Carlo methods. His pioneering work on multi-level Monte Carlo has broad applications in computational finance, uncertainty quantification, and many other fields. And today he is going to tell us about optimization of multi-level Monte Carlo on FPGA. Please take it away, Mike.
Thank you very much, Sifan. And so let me start by saying that this is work done by my student, Irina, who's also on the call and is waving to you from her camera at home. So yes, optimization of multi-level Monte Carlo on FPGAs. This is the outline of what I'll be talking about, but let me just jump straight in by talking a bit about FPGAs. Okay. So I'm not expecting very many of you to know much about FPGAs. So in general, most of you will be computing on traditional CPUs. A few of you may be working with GPUs. So those are the two dominant platforms in scientific computing these days. Both of them doing floating point arithmetic, double precision, single precision, and increasingly even half precision. But what we see with the way the hardware trends are these days is that whereas in the past, every couple of years, for the same amount of money, you could buy a machine which had twice the compute capability at the same power level, the same wattage. These days, the improvements in chip performance are coming from the chips themselves just getting bigger, with more and more cores in them. And so the performance is going up, but so is the power consumption and so is the cost. So if you look at performance per watt or performance per dollar, things are improving much, much slower than in the past. And so that means that it prompts us to look at other computing technologies. And FPGAs, field-programmable gate arrays, they're a technology that's actually been around for a long time, at least 30 years. But so far, it's had relatively niche applications. Although it's significant enough that both Intel and AMD bought the two leading companies in the area. Now, potentially, they're highly efficient for low precision fixed point arithmetic. And I'll talk later about the difference between floating point and fixed point arithmetic. But they consist of millions of logic blocks. And you write a program which gets mapped onto these logic blocks. And in particular, because there's very little sort of built in as a starting point, you can control for each individual variable in your calculation how many bits you use to represent that variable. And so by going to really very reduced numbers of bits, there's a potential for highly efficient calculations on them. And with multi-level, as you might guess, we can use multi-level to correct for the errors due to the low precision computing. And so I think this is a sort of ideal combination, multi-level plus FPGAs, and all aimed towards the computational finance application. Okay, so this is maybe the sort of killer application that FPGAs need to really break through into the mainstream of scientific computing. So what we're interested in doing in computational finance is approximating the solutions of SDEs, stochastic differential equations. And here I've written one down in a sort of scalar SDE form. Okay, so dw is the increment of a Brownian motion. So over an infinitesimal time interval dt, that's normally distributed with a variance equal to dt. And we approximate this, the simplest way is using an Euler-Maruyama discretization, where we freeze the drift A and the volatility B at the start of the time step. And then we multiply the drift by the time step h. We multiply the volatility by the increment delta w for the Brownian motion. And then in simple applications, what we want to do is to estimate the expected value of some financial option P, which depends, in the simplest case, on the final path value coming out of the SDE simulation. Okay. So Monte Carlo methods are incredibly simple. We simply do n independent samples based on independent random inputs for our SDE simulation, and we take an average of those values. And so that gives us a y, which is an estimate for the expected value of p hat, this numerical approximation. If the samples have a variance of v and a cost per sample of c, then to get epsilon root mean square accuracy, the number of samples we have to take is roughly epsilon to the minus 2 times the variance v. And then the total cost is that times c. So we have epsilon to the minus 2 vc. Okay. Okay, so now we come to the two-level Monte Carlo, the simplest version of multi-level. That if we want to estimate a quantity expected value of P1, but it happens to be much cheaper to simulate a P0, which is approximately equal to P1, then we have this trivial identity that the expected value of P1 is the expected value of P0 plus the expected value of the difference. And now, rather than using Monte Carlo to estimate the quantity on the left, we use Monte Carlo to estimate each of the quantities on the right-hand side and to estimate them separately, independently. So we have n0 samples being used to estimate the expected value of P0, and we have n1 samples being used with completely independent random numbers to estimate the difference, P1 minus P0. And why is this good? Well, n0 will be comparable to the number that we would normally use, but each of those P0 calculations is very cheap, has a very low cost. If P0 really is a close approximation to P1, then P1 minus P0 is small, and therefore its variance is small. And therefore, we don't need a very large n1 to accurately estimate the expected value of the difference. So what we can now do is to optimize the number of samples, n0 and n1, and we can again get that epsilon root mean square accuracy, but now the cost behaves like this. So epsilon to the minus 2 times the square of the square root of v0 c0 plus the square root of v1 c1. Okay, where the v's and c's are the variances and costs that are listed there in the slide. Okay, so that's the two-level method. We then very naturally generalize to having a whole sequence of levels. And this is what we would do normally if we're approximating an SDE, that on level L, we might use 2 to the L time steps. So as we go to finer levels, we're doing more time steps. It's more accurate, but it's also more costly. Okay. So we have the expected value of P on level capital L, the finest level, is the sum of expected corrections, with P hat minus 1 defined to be 0. so that initial delta P0 is really just P hat 0. Okay, so we have independent estimation for each level of correction. We optimize how many samples we use on each level, and we end up with the total cost behaving like this. Epsilon to the -2 times the square of the sum of the square roots of VLCL. Okay, so that's a natural generalization of the two-level method. Okay. So now for the FPGA work, what we're going to do is use nested multi-level. So we're going to start from the usual time-stepping multi-level. And then when we're wanting to estimate each of those expected corrections, we're going to do it twice. We're going to do it inaccurately on the FPGA, and then we're going to do a correction to get back to full accuracy. So what we have there on the left is NL samples on level L, using a delta P hat with a tilde over the top of it. And that tilde over the top represents the fact that it's approximate, that we're doing it as a low accuracy fixed point calculation on an FPGA, potentially using 8 bits or fewer for all of the variables in the calculation. And then on the right-hand side, we have the correction between delta PL being computed on the CPU and delta PL approximate being computed on the FPGA. And those will both be using the same uniform random number as input to the calculations. And that uniform random number is then used to generate a normal random number. So I'm about to say a bit more about that point in a few slides' time. Okay. And then again, you optimize the number of samples on each level and the number of samples on the FPGA alone versus the number of samples for the correction. And we end up with this expression for the total cost. Okay, so here, CL tilde, that's the cost of the cheap evaluation of delta PL. So that's the thing being done on the FPGA. And the V tilde, that's the variance of the difference between the inaccurate FPGA calculation and the accurate CPU calculation. Okay, and so what we expect is that C tilde is much less than C, and V tilde is much less than V. That's kind of the point. Oh, please, by the way, if you have questions, do raise them. I'm looking at the chat in front of me, so I'll see that.
Oh, actually, there is a question on the slide 6.
Oh, yes, let me go back to that. Yep.
Yeah, so the question is, are P0 ON and the P1 1N correlated?
No, so 0 and 1 is meant to indicate that they're completely independent sets of random numbers. So the random numbers that we use for the correction, estimating the difference P1 minus P0, we use an independent set of random numbers from the ones that we use to estimate the expected value of P0. And using that 1, n for both P1 and P0 emphasizes the fact that we use the same random numbers for both P1 and P0. That's the thing that keeps the two of them close together, so that the variance between them is very small. Okay, for some reason, I'm not seeing that message in the chat, so I'm not sure why that is.
There's a separate button that says Q&A, which might help you see the...
Oh, I see, right, yes. Oh, okay, thanks. I do agree with the comment about one might wonder whether option pricing is such an important goal for humanity. It is one of my reservations with the finance industry is the sheer amount of human potential that goes into the industry that you do wonder whether it might be good for a bit more of it to go in other directions. Okay, so right. So I think I've finished that. Okay, so on level L, this is just slightly rearranging things. So on the right-hand side, what I have is the square root of VLCL, which is what we would normally have, and then multiplying this sum of two square roots. So it really sort of highlights that what we want to achieve here is a CL tilde that's much less than CL, but also a VL tilde that's much less than VL. And so there's an optimization trade-off here that making VL tilde very small would suggest that we use more bits in the calculation. But doing that is going to drive the cost up for C tilde. Okay, so we have to kind of find the sweet spot. And then what are the two things that we're adjusting here? Well, the first thing is the way that we generate the normal random variables from the original input uniform random variables. So that's an important part. And then the other thing is in the FPGA calculation, we have the flexibility to choose how many bits we use for different variables. Now, we don't have to use the same number of bits for all variables. And so let's see how we can exploit that flexibility and perform the optimization. Okay, so given some method for generating uniformly distributed random numbers between 0 and 1, and there are lots of ways that they can be generated very efficiently on both CPUs and FPGAs. So in fact, the FPGA architecture is well sort of set up for doing uniform random number generation. Then I would say that these days, the usual way of converting from uniforms to a normal random variable is through the quantile function. So having z equals q of u, where q is the inverse of the normal CDF function. You know, longer ago, other techniques were used like ziggurat and polar method and things. But these days, I think most of the fast implementations now approximate the inverse of the normal CDF. So on the FPGA, we're going to do that. But if on the CPU, we're doing random number generation where we're using U, which is maybe, say, 32 bits, we're only going to use the leading D bits for the FPGA calculation. And that's going to be one of the things that we optimize. Okay. And then that's going to give us an approximation, Q tilde. Okay. So this is where you read the literature and you have a ponder. And there are various ways in which we can convert uniform random numbers into approximate normals. And the key thing here is we want something which will be cheap to implement on the FPGA. So one option is to just have a simple lookup table. That if we have D bits, that corresponds to taking our interval from 0 to 1 and breaking it up into intervals, all of size 2 to the minus D. And then we can use those D bits just to do a straight lookup in a table. The issue with that is if we're getting up to a D of 10, 12, 14, that could be quite a big lookup table. and I fear that that might be rather costly on the FPGA. So we haven't yet done real FPGA calculations. So this is something that we will have to look at in future work, working with colleagues who have experience in FPGAs, because programming those is really very different to programming CPUs and GPUs. But right now, my guess is that that is not a good choice. One of the things that's bad about that is the inverse CDF function is singular near u equals 0 and u equals 1. So another way of approximating it is to do it on what are referred to as dyadic intervals. So intervals which get smaller and smaller as you approach 0. Okay, so think of this as approximating the bit that goes from 0 up to half. Okay, so this is an interesting approach. It's been used in the past on FPGAs. It's also the basic approach, I think, that Intel uses in their mathematical libraries for running on Xeon processors using AVX 512 vectorization. Except that rather than being piecewise linear, it'll be piecewise, well, at least cubic and probably higher order than that. And then another method, which I suspect may give us, the best overall performance, is what I'm referring to here as a two-variable method. So we take d bits of input and we split it into two parts. So each part has a signed bit and then d over 2 minus 1 other bits. And they get used for a lookup table to basically handle the bit going from 0 up to half. And what that gives us, by having two pieces, it gives us two normal or approximate normal random numbers, Z1 and Z2, but we choose those to have a variance of approximately half. And then what we return is the sum, Z1 plus Z2. And so that's then something that has approximately a variance of 1, which is what we want. Initially, you can set up the lookup table with values that come from this best piecewise approximation, but then you can actually optimize that and further improve it. And you'll see the benefits of that on this next slide. Okay. So on the left, what we're plotting here is the mean square error. So this is the expected square of the difference between the approximate normal random number and the true random number. True being, defined by the CPU operating in single or double precision. Okay, and then on the x-axis is the number of bits that we are using in the FPGA implementation. The solid line there is using the full large lookup table. The dotted line is the two-variable method with the initial values, but then the dashed line shows the two-variable method with the optimized values. And so actually it's surprisingly good and really needs a very small lookup table. And then the sort of dashed dot line, that's the one using the dyadic intervals. So it's good for very few bits. It could be changed to be more accurate for a large number of bits. But overall, I think the two-variable technique is going to work out really nicely. And so that's currently our best guess as to what will work well on the FPGA. Okay, so let's talk now about fixed point variables. So a floating point number has a representation like this. We've got a sign bit, S, so S is either 0 or 1. We have an integer exponent, E, And then M is a mantissa, which lies somewhere between 1 and 2. Okay, so you can take any floating point number and put it into this format. And in floating point arithmetic, it's storing the integer exponent e as well as the mantissa m. And so, the value of the exponent will change as the calculation proceeds. Okay, and they're all stored together in a 32-bit or a 64-bit variable. Now, fixed point numbers are very similar, except that the exponent e is fixed. It's sort of hard-coded in your program. And so if you have d bits, not including the sign bit, which you may or may not need for the variable, then you represent your variable as -1 to the sign bit times an integer n, which is between 0 up to 2 to the d minus 1 times 2 to the e minus d. Okay, so the biggest number you can represent then is just below 2 to the e. So you choose the exponent e based on what range you need for your variable. That if you run your program, you know what's the largest value that that variable ever takes. And so that's how you choose how big e is. And then d, that's something that we can optimize on, choosing how many bits, how much accuracy we want for the fixed point variable. Okay. Now, when we do an optimization, we're going to need a model for the cost and a model for the error. So when you're adding two numbers together, the cost is roughly proportional to the average of their lengths. I mean, if you think the way that you would sort of manually add two numbers together, hopefully that seems sort of intuitively natural as a cost. And there is a limited amount of literature, based around using this cost. And then when you calculate the answer, you then round it to the nearest number that can be represented. And that rounding error, well, if I go back to the previous slide, I said here that n has to be an integer. Okay, so if we round to the nearest integer, then there's going to be a rounding error of 2 to the e minus d minus 1. And so that's where that's come from on the next slide. Okay. And that subscript c is just to say that this is the exponent and the bit width for variable c. Okay. And then when we're multiplying two numbers, a times b, the cost is roughly proportional to the product of their lengths. And again, if you think of the way that you perform, multiplication manually, so write out the whole long laborious way you learned to do it in primary school, hopefully again that's sort of intuitively natural. And we choose to bound that instead being 1/2 of the average of the squared quantities. And I'll explain on the latest slide why that's a convenient way to do things. Okay, and again, the rounding error is bounded by that same number. Okay, right. So we have a calculation that's computing an output p. And along the way, we're making rounding errors because we have finite precision arithmetic. So what we want to know is how big is the error in the final computed p given these rounding errors at each stage in the calculation. Okay. Well, to leading order, so linear treatment says that the error delta p is the sensitivity dp dx times the rounding error delta x. Okay, and I'm using the notation that's standard in the automatic differentiation community, So using x bar to represent this dp dx. Okay, and so we can evaluate these sensitivities of the final output to errors in each of the intermediate variables by doing adjoint sensitivity analysis. So just like backpropagation in machine learning, just like doing adjoints for computing Greeks in computational finance. And so it means that we can very efficiently compute all of these sensitivities to every single one of the intermediate variables within our calculation. Okay, so those errors and sensitivities will vary from path to path because each path has a different Brownian motion, different input random numbers. Now, there's then a question of whether the errors that we incur at different points in the calculation, are they correlated or uncorrelated? Okay, so the worst case assumption would be to say that there's possibly full correlation between each one of the rounding errors. In that case, we would have to bound the error this way by saying that the square root of the variance of the error in the output is a sum over all of the intermediate variables of the variance of the error due to that variable. And then that's bounded by the expected square of the sensitivity times this size of delta x being 2 to the e minus d minus 1. But that's very much a worst case scenario. The alternative is to model the errors as being statistically independent. Now, there's no particular reason mathematically to think they have to be statistically independent, but we're just saying let's take that as a model and let's see how useful this model is. Okay. Furthermore, let's take the rounding error as being uniformly distributed over that range from minus 2 to the e minus d minus 1 to plus 2 to the e minus d minus 1. And if we do that, then the variance of the final output is a sum of the variances of each of the intermediate errors. And that's bounded then by the expected square times 4 to the e minus d divided by 12. So that 12 number comes from working out what the mean square error is for this uniformly distributed rounding error. Okay, so we have these two models for the error, one very much worst case, the other to some extent best case. So we then go and do a test to see which of them is a more reasonable model. So here we're doing geometric Brownian motion, the simplest possible test case. We're doing the multi-level in time. So we have SL being the fine path, SL minus 1 is the coarse path. So the fine path is using a time step of h. We've got a couple of constants, con1 and con2. And then we have this path calculation where we're looping over all of the fine time steps. In computing the drift and volatility for the coarse path, we only update that every second fine time step, the beginning of every coarse time step. So that's what that sold bit is doing. And then I've really expanded out the algorithm so that each line just has a single arithmetic operation. So you're really seeing each and every intermediate variable in the calculation here. Okay, and for all of these variables, we will be using the adjoint error analysis to work out what the sensitivity is to errors in that variable. Okay, and then at the end, we compute the sort of classic multi-level delta P, taking the difference. This is for a simple European call option, difference between the level L approximation and the level L minus 1. Okay, so here now we have simulation. So I said that we haven't actually used any FPGAs yet. What we've done here is these are simulations using the FPGA sort of simulating capabilities of MATLAB. So MATLAB has a fixed point toolbox, which is designed to help people to design FPGA code. We haven't investigated using that to actually generate real FPGA code. I think we'll actually use other techniques for doing that when it comes to the real FPGA work. But it does give us, for this mathematical study, the ability to simulate FPGA calculations so that we can see what the accuracy is. And so here, what we're doing is we're using the same number of bits for all of the variables, and we're increasing that number of bits from 4 up to 12. The line with the symbols, these are, the numerical results from the MATLAB calculation. So this is the variance of the difference between delta P on the CPU and delta P on the FPGA using this reduced number of bits. And then the two lines, one of them is using the pessimistic dependent bound, and the other one's using the optimistic independent bound. And so what we see is that the independent bound is much closer to the true behavior. So these are the numerical results for level 0, when actually it is just the P0. There isn't any delta P. And then the next slide is from level 4 in the calculation. And again, the independent bound is a much better model for the actual behavior of the reduced precision calculation. Okay, so on the basis of those results, then, we use this as the error model, that we have a sum over all of the working variables of the expected square of the sensitivity calculated using the adjoint methodology times this quantity, 4 to the e minus d divided by 12. So again, remember that the exponent e is fixed for each of these variables based on what the range is that's needed. But the bit width d, that's something that we can control. Okay. So if we use the same number of bits for both of the s's and for all instances of these other variables, then this gives us an error model which involves a sum over 7 terms of some constant times 4 to the minus dk. Okay. And then for the cost model, we just count up how many different additions and multiplications involve each of the variables. And what we get is this corresponding quadratic cost model. So AK here is the number of additions involving variable k. MK is the number of multiplications. And here's where we benefit from that alteration I made with the cost model for the multiplication. Because what this is giving us is a sum of 7 terms, each of which depends only on one particular dk. So there's no cross product between different d's. And that makes the optimization easier later on. Okay. Also in this, we're ignoring the error and the cost due to the approximate normal random numbers. I'll say a bit more about that later on. But really, on the cost side, we don't know how to sort of come up with a meaningful cost model for that. Okay, so now what we want to do is to minimize this quantity, which appears in the overall cost, for a given value of VL, which we know from our simulation, and we arbitrarily set the CL to be 10 to the 4 per time step on the CPU. And this really is a somewhat arbitrary choice. So right now, it's very hard for us to say what is, in a sense, the comparative capability of the FPGA and the CPU. That we have to come up with some number that represents, the some relative performance. We think that's a reasonable number. Once we get onto the real FPGA calculations, it will be interesting to see what number we get there. Okay, so we want to optimize that quantity at the top. So we just differentiate with respect to dk and set the derivative to 0. And so what that gives us is the equation that's given there, where lambda has the value on the line below. So that gives us the optimal trade-off between cost and variance. And now what we can do is an optimization where we vary lambda to find the optimum. For each lambda, we can solve that equation to get the optimal dk. And we can do that independently for each variable. Okay, and then we just adjust lambda to perform the global minimization. So it turns out that the optimization process is very straightforward and, importantly, would scale very well to much more complicated applications that have a huge number of intermediate variables. Okay, so now here are some comparisons. So this is how that quantity behaves as a function of lambda. And so it gives you an idea of what we're having to do for the optimization process, that we're trying to find the minimum. The dashed line there is what happens if, rather than optimizing each variable independently, we just say that all variables have the same number of bits. Okay. So what it shows you is that on level 0, there's really only modest benefits from doing the optimization. I must say, I'm a bit disappointed that it's not greater savings on level 0, but it is what it is. I mean, that's the point of doing research, is to find out how much benefit you get from the optimization. On level 8, we see a more significant benefit from the optimization. So there, again, we've got the uniform and we've got the optimized, and then the optimization will find the optimal value of lambda. So it'll find the minimum on these curves. This then shows how the optimal number of bits varies for different variables as we go through the different levels of the multi-level. Okay, so let's talk through the key points here. So the dashed line here is the optimum bit width when all variables have the same width, the same number of bits. Okay, and then we have separate curves for each one of the other variables in the calculation. So we see that we need the greatest accuracy for the values of the path itself, S. And that's to be expected, because you're constantly adding a small quantity to S as the path evolves. And you want to make sure that you're not losing a lot of that, extra delta S that's being added on. And so S needs a large number of bits. What we're seeing is that at level 0, because the true calculation has a relatively large value, then the approximate calculation doesn't have to be very accurate. But by the time we get down to level 10 in the multi-level, the true value of delta P that we're computing on the CPU, that's a very small quantity. And therefore, we need a lot more bits on the FPGA to get a reasonable approximation to it. Okay, so that's why the number of bits changes as we go to finer and finer levels. And it's possible that once we get on to doing real calculations, that we may only want to use FPGAs, for the first, 4 or 5 levels, and after that, we may not bother using the FPGA at all. We may just do the CPU calculation. We'll see about that once we get on to the real applications. And then this is the value for that sort of optimal cost on each level. But when I say cost here, it's the sum of the 2 square root terms. Okay. So we're not seeing a big benefit on level 0, but we're seeing larger benefits on the higher levels. So really, at this point, to conclude, we've taken this whole mathematical development and optimization really as far as we can without doing a true FPGA implementation. Now, I said at the beginning that the overall cost is epsilon to the -2 times the square of this sum. So taking this to be the overall cost, and given our assumption, which is somewhat arbitrary as to the relative costs of FPGA and CPU calculation, what this is giving us is approximately a reduction factor in the overall cost of 15 if we use uniform bit widths on each level, and then 24 if we use the optimized bit widths, so different variables having different bit widths. Oh, sorry, if I go back 2 slides, I forgot to mention the solid line there for RNG. This corresponds to how many uniform random number bits we need to use for the random number generation using the 2 variable methodology on the FPGA in order for the errors due to the random number generation to be smaller than the errors due to the rounding errors of everything else. Okay, so again, we need more accuracy with random number generation on the finer levels than we do on the coarsest level. Okay, but in terms of this cost saving, that's ignoring the cost of generating the random numbers. But I think that 2 variable approach will be very efficient on the FPGA, and so really should have minimal cost, I think. Okay, which then brings me to the long list of future work. So we've gone as far as we can mathematically. Now we need to actually do calculations on FPGAs, and when I say we need to do that, I'm talking to people I've collaborated with in the past who are computer scientists who are now doing work with FPGAs to see if they or their students, postdocs, will actually carry out the implementation, probably on AMD hardware, using AMD's high-level C++ programming support. So, we need to assess the different ways of generating the normal random numbers, see what the cost is. We need to check whether the cost model that we're using currently for the optimization is that a reasonable cost model, or maybe we need to work on that and improve that. Then we need to implement the CPU side of the algorithm so that we get those corrections, from the inaccurate FPGA to the accurate CPU implementation, and then validate the whole sort of telescoping sum of the multi-level to finally get overall cost savings. And then, having done all of that on the FPGA, this is something which I'll maybe do myself, is look at doing similar work on GPUs, maybe also on CPUs, doing half precision. Because of the rise of AI, the half precision floating point capability of CPUs and GPUs is really very impressive. And so, to be fair, we really ought to see what they're capable of using half precision as well as single precision. And then once that's all done for geometric Brownian motion, then clearly there are applications to extend that to other SDEs. Okay, so a few references. So Irina's MSc thesis is available from my webpage, my usual multi-level community webpage. The second one is the one that talks about doing the random number generation using these sort of non-uniform intervals, the dyadic intervals. The third one I haven't mentioned is some other work that's been done previously on multi-level on FPGAs, but there they were using uniformly high accuracy random number generation. And that really hit the computational savings that they were able to achieve. And then the fourth reference is some other work I've done with a previous PhD student developing analysis of the effect of using approximate normal random numbers within multi-level. Okay, so there I'll finish, and we've got some time for questions.
Thank you very much, Mike, for the interesting talk. If there is any question, please feel free to use the Q&A button or the raise hand button to ask. Yes, Fred, you can unmute yourself.
Thank you, Mike. Very nice talk. I remember how we got all excited about multi-level methods when you brought them to the fore some time ago. And now I'm wondering if we're going to get excited about FPGAs. I'm wondering how you think that it's going to go in terms of, I've not gotten to the point of getting my students on GPUs yet, because maybe that's my problem and not theirs. But this is another leap, and the tuning that has to happen. Do you think it'll become more automatic, or do you think that it's just inherently will require a lot more hands-on?
Working with FPGAs is tough, I would say. Traditionally, they were programmed using a language called VHDL, and essentially only electrical engineers touched it. So it was really striking in the early days of GPUs that you'd have mathematicians talking about using GPUs, but it was electrical engineers who were talking about using FPGAs. I would say that right now I have a degree of excitement about the possibility here, but I would say until I'm able to actually demonstrate it on real hardware, I would temper that excitement. I think it's going to take a significant amount of work to actually realize these benefits. With FPGAs, I came to Oxford in 1992, And the computer science colleague at that time told me, Mike, this is great new technology. It's going to completely revolutionize scientific computing. And he was talking about FPGAs. So it hasn't happened for 32 years. That doesn't mean to say it won't happen, but it does temper my enthusiasm. So I think potentially this really is a kind of best case scenario. So I almost feel like saying that if FPGAs aren't good for this application, then I really wonder what on earth they are going to be good for in terms of scientific computing. So yes, we'll see just how quickly we're able to get on to doing actual FPGA implementations. Right now, I'm helping a colleague to draft a research proposal to get some funding to do this. But that then means it's probably going to be at least, I don't know, 18 months away, 2 years away. So I would say watch this space. I think it's definitely worth being aware of the half precision capabilities of CPUs and GPUs, because that's much easier to use. Although again, there are issues as to how best to do the random number generation, which I think are interesting questions. So, I mean, GPUs really are pretty easy to use, I would claim. Doing the half precision is slightly less easy.
Thank you for the encouragement, Mike.
Okay.
If you think they're easy, then maybe they're within my reach, but I'm not sure.
Well, I've got a web page where I've got a 1-week course on GPU programming.
Okay,
complete
that's what I need to look at.
With lecture slides and practicals and things like that.
Guanyang?
Oh, yeah. Hi, Mike. Very nice talk. Very eye-opening, actually. So I have a question on the normal random number generator, because like I don't have that bottom level of implementation, but I'm curious because I feel I would thought that people would use like a box Muller like algorithm or transformation to generate random number. So can you comment on why those methods are worse in terms of the actual implementation comparing with the inverse CDF?
So on the CPU, box Muller is still an option, but I think now that the inverse normal CDF is faster than the box Muller. Because of doing it with these dyadic intervals. Intel doesn't come out and really say exactly how it does things, but you know, I found a couple of clues in conference presentations by Intel engineers that seem to suggest that's what they're doing. Yeah, it's just a box Muller's. It's got the log and the cos and the sine and everything, and they're expensive operations. Whereas with the dyadic intervals, you're looking at maybe third, fourth, fifth order polynomial on each of these little intervals. And the key thing is using the vector capabilities of the CPU allows you to basically use vector registers for the lookup table. And that's what makes it so efficient.
Yeah, thanks a lot. Yeah, that's very good to know.
I actually have a quick question. So you described your algorithm for simulating the geometric Brownian motion. I wonder, does the algorithm depend on how you construct the Brownian motion? Like if I use a Brownian bridge construction, does it change anything?
Not in principle. I mean, you're again needing normal random variables, and so you could use that. So if for example you were doing quasi Monte Carlo and using a Brownian bridge construction, then that's all in principle fine. Yeah.
Okay, but the analysis is probably different because the sensitivity is different if you use a different.
Well, the methodology is still the same.
Okay,
you still have a code which has lots of intermediate variables and then produces an answer at the end. And so you can still use the adjoint sensitivity analysis to go back through the calculation to get the sensitivity of the final output to rounding errors at each stage in the calculation. So the methodology still works. I mean, the code is clearly different, but the adjoint methodology works in any application. And so the adjoint capability is really crucial here, so that if we go to applications that have very large numbers of intermediate variables, then the cost doesn't get ridiculous. Because the adjoints give you these sensitivities very cheaply.
Thanks. If there is no more question, then I guess that's it for today. Thank you again, Mike. And just announcement for next week. Next week we'll have